Imagine the intense deadline pressure of your Cambridge computer science exam. The clock is literally ticking down. Your heart is racing. You're staring at a massive, multi-part networking question, and you need to break down the raw story of the problem and deliver the exact headline the examiner is looking for. Today, we are uncovering the strategic blueprint for copper cable characteristics and networking to help you secure absolute top marks. And listen, whether you're building foundational knowledge in the IGCSE or O-level courses like 0417, 0478, 0983, 0984, or 2210, or you're stepping into the high-stakes arena of the advanced A-level 9618 paper, the core strategy remains the same. To set the stage, let's look at two typical candidates we see struggling every single year. First, we have Alex. When Alex is faced with a question about copper cable transmission, he completely panics and just overloads the page with raw computer science facts. We're talking a massive, unformatted block of text about everything from plastic insulation to the history of Ethernet, but he includes absolutely zero analysis. Then we have Sam. Sam looks at the clock, realizes he's behind, rushes through the paper, and completely misses the specific command word requirements. He ends up answering describe when the examiner explicitly asked him to evaluate. Both of these students are leaving massive marks on the table. Today, we are going to look at their flawed approaches, grab our red pens, and lay out the exact strategy to turn those errors into a guaranteed A-star performance.
Here is our exact blueprint for today. We'll start with the A-star networking gap, then master core concept application, dive into the method mark strategy, highlight the top examiner warnings, and finish up with evaluative thinking.
All right, let's jump right into Section 1, the A-star networking gap.
Now, what's really fascinating about this quote is hearing directly from a senior examiner about the immense, almost unfair weight this single conceptual framework carries. You might be wondering, out of the entire massive Cambridge computer science syllabus, why are we zooming in on copper cables? Why not routing protocols or database normalization? Well, the answer is that this specific topic sits right at the critical intersection of physical hardware limitations and theoretical data transmission. It is literally designed to be a discriminator topic. It's there to stretch you and separate the average candidates from the truly exceptional ones. Look, a B-grade candidate can tell you that copper cables are cheap and widely used, but that's just raw, rote memorization. An A-star candidate? They can explain exactly why the twisting of wire pairs and unshielded twisted pair cables cancels out electromagnetic interference through destructive interference. And they can explain how that directly impacts the maximum viable length of the cable before signal attenuation corrupts the binary payload. That level of technical depth is exactly what the Cambridge rubric is hunting for.
So, this brings us to the core challenge we need to solve today. When data travels across a copper cable, it isn't traveling as magic ones and zeros. It's traveling as physical voltage changes over time. Interpreting this complex binary representation requires you to map abstract digital logic onto messy physical analog signals. And before we reveal the ultimate framework to solve this, I need you to do something. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to it. Students struggle here because they fail to connect the mathematical theory to the physical constraints. When an examiner presents a chart showing a degraded electrical pulse, candidates, like our friend Alex, completely freeze. They forget that signal attenuation, jitter, and latency all combine to skew that perfect square wave into an unrecognizable mess, leading to bit errors. To secure top marks, we are going to use the PEL framework: point, evidence, explanation, and link. This is how you confidently extract data from graphical binary representations, understand the threshold voltages that define a 1 versus a 0, and articulate exactly how copper characteristics cause those signal distortions in the first place.
Let's move smoothly into Section 2, Mastering Core Concept Application. Remember our candidate Alex? Alex memorized the entire textbook chapter on network hardware, but when the exam asked him to analyze the suitability of copper cabling for a high electromagnetic interference factory environment, his answer was just a generic list of features. It was superficial breath. He wrote, "Copper cables are used in LANs, they suffer from attenuation, and fiber optics are faster." Notice how that touches on multiple things but actually explains nothing? Cambridge doesn't want you to just regurgitate facts. Let's transform Alex's answer live right now using the PEL framework to achieve analytical depth. Point: unshielded twisted pair cables are highly susceptible to crosstalk. Evidence: electrical signals in adjacent wires create fluctuating magnetic fields. Explanation: if the twist rate is insufficient, these fields induce unwanted currents leading directly to data corruption. Link: Therefore, in a high-density server rack, shielded twisted pair or STP might be strictly necessary to ensure data integrity. Do you see the difference there? That second answer drills all the way down into the actual physics and logic of the network. It's a game changer.
You absolutely must be able to take established principles, like the systematic peel analysis we just did, and confidently apply them to completely unfamiliar contexts. Cambridge examiners love to throw curveballs. They're not just going to ask you about a standard, boring office network. They're going to ask you to design a topology for a research station in Antarctica, or a manufacturing plant with heavy robotic machinery generating massive electrical noise. If your understanding of copper cable characteristics is truly connected and conceptual, you won't panic when you see the words manufacturing plant. You'll immediately decode the story. Heavy machinery means high electromagnetic interference. High EMI means standard UTP copper will suffer severe data corruption. Therefore, my analysis must focus on shielding, grounding, or recommending fiber optics as an alternative. You are connecting the physical environment of the unfamiliar context directly to the physical properties of the networking medium.
All right, moving into Section 3, the method mark strategy.
Stop scrolling! Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's talk about saving Sam. In Cambridge Computer Science, the final answer is only a tiny piece of the puzzle. Sam rushed the math on a bandwidth calculation question, made a tiny arithmetic error in step 1, and scored a straight 0 because he didn't show his working. The method mark strategy is your ultimate safety net. Here are the 5 exact sequential steps you must follow every single time. Step 1. Deconstruct the command word. Is it identify, describe, explain, or evaluate? Step 2. Extract relevant data. Highlight constraints right there in the prompt. Step 3. Select your analytical framework, like our trusty peel structure. Step 4. Execute with clear notation. If you're calculating transmission delays over a 100-meter copper link, write down the formula first, substitute the value second, and solve third. Step 5. Present with correct terminology. Don't ever say the signal gets weaker, say it experiences attenuation. By enforcing this strict discipline, you completely eliminate careless errors.
Now, you might be scratching your head thinking, what do practical programming skills have to do with the physical characteristics of copper cables? The answer is literally everything. In the real world, the physical flaws of copper, like noise and bit flipping, absolutely require software solutions. When you're writing networking code, you must design algorithms that can handle imperfect physical transmission. You need to implement error-checking solutions like parity checks or cyclic redundancy checks to detect when a 1 has been randomly flipped to a 0 by electrical interference. You must test these algorithms thoroughly against edge cases, like sudden burst errors. And finally, you have to evaluate performance. Does your error correction algorithm add too much latency to the network? Understanding the physical flaws of copper is the exact foundation that informs the logical design of your algorithms.
All right, it is time for an interactive workshop. Challenge number 1, the data scan. Imagine a complex computer science data table on your screen right now. You have a 60-second timer ticking down in your head. The columns show frequency in megahertz, and the rows show attenuation in decibels per 100 meters for different categories of copper cable. Scan that data. What happens to the attenuation as the frequency increases? If you're applying our strategy, you'll quickly identify the core trend. As frequency goes up, attenuation increases significantly, drastically reducing the effective range of the cable for high-speed data. Boom. That's data interpretation in action under pressure. You aren't just looking at numbers, you are extracting the hidden narrative and using it to formulate an ironclad, evidence-based conclusion.
Let's transition into Section 4, Top Examiner Warnings.
We are moving right into challenge number 2 of our interactive workshop, Find the Flaw. I'm going to give you a flawed sample paragraph, and I want you to spot the sentence that is bleeding marks. Here we go. Copper cables are highly effective for long-distance wide area networks. They use twisted pairs to reduce crosstalk. However, boundary conditions like maximum cable length must be considered. Did you catch the massive flaw? You've got about 10 seconds. Okay, it's that very first sentence. Copper cables are highly effective for long-distance wide area networks. No way, absolutely not. Due to severe attenuation over distance, fiber optics are the standard for WANs, not copper. This is mistake number 3 on our list, failing to provide an answer specific to the correct context. Candidates constantly mix up local area network physical mediums with wide area network mediums. Furthermore, mistake number 2, Forgetting edge cases is rampant. Always explicitly state what happens at the absolute limit of that cable's physical range.
This brings us to challenge number 3, speed writing. You have 30 seconds on the clock to write one perfect PO paragraph defining key terminology. Candidates constantly throw buzzwords around, so you must always define your terms clearly before expanding on them. Think about how you would define crosstalk under pressure. Many students will just write, "The cable should be shielded to stop crosstalk." That is way too vague. The examiner doesn't know if you actually understand the physics. Instead, apply the framework and explicitly define it. Write, "Crosstalk, which is the unwanted transfer of signals between communication channels due to electromagnetic interference, can be mitigated by shielding." By defining the term directly in the sentence, you instantly lock in that knowledge mark before you even begin your analysis.
Let's bring it all home with Section 5, Evaluative Thinking for top marks.
Everything we've discussed today culminates right here in the final computer science answering system. To guarantee top marks, you must follow 3 golden rules: command word decoding, PO framework application, and a strict time management matrix. When a command word asks you to evaluate, discuss, or justify, simply listing facts captures your grade. You have to step up and play the role of a senior network engineer. Let's look at this table. First, consider multiple solutions. If the question is about wiring an office, you must compare UTP to STP and fiber. Next, analyze the trade-offs. UTP is incredibly cost-effective, but the massive trade-off is high vulnerability to EMI. Third, acknowledge limitations by identifying edge cases, like the strict 100-meter limit on standard copper Ethernet. Finally, justify your decisions. You conclude by stating, despite the vulnerability to EMI, UTP is the recommended solution for this standard office environment because the budget constraints heavily outweigh the negligible risk of interference. That right there is A-star evaluative thinking.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries. But, and this is a big but, that only happens if they practice consistently with our weekly videos. Knowing the theory is just step 1. You have to take this method mark strategy, sit down with a blank piece of paper, and run these drills under timed conditions until extracting binary representations becomes second nature. Here's your final reminder: subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. I'll leave you with this final provocative thought. Knowing these examiners' secrets is only half the battle. So how exactly will you apply them to your very next practice session? Will you fall back into the trap of superficial breadth, or will you deploy our analytical framework and prove your technical depth? Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.